Welcome everybody. This is session number 8 of the course Mathematical Methods of Signal Processing, and we are continuing to discuss the topic of impulse response, coming closer to transfer functions and so on. I thought it's a good idea to recapture a little bit the terms and the key players that we have used so far. So we started to discuss this algebra, the complete algebra, so it's called the Banach algebra with respect to pointwise multiplication, which is 0 of RD. It takes the role of simple version of test function spaces, and in our finite dimensional example, it was the role of the cubic polynomials. It contains the compactly supported functions as a dense subspace, and all these functions which have compact support are also Riemann integrable, which is quite useful later on. Then we realized that we need the linear functionals on such a Banach space, and they are also forming a Banach space with the natural norm, which is the size of a linear functional. This is the dual space, also called the space of bounded measures. The terminology, the word measure, is justified by the Ries representation theorem, which means in functional analysis or measure theory courses, you will learn about these functionals as integral over Rd, f of x, d mu of x. Now, the key to convolution is the identification of the translation invariant linear bounded operators, so the continuous operators from C0 into C0, which commute with translation. If you keep in mind that physical laws are time invariant, that's one of the reasons why such systems are so important in applications. Now, every such system is already like a moving averages, well determined by knowing what it does at the origin. And the mapping on the second part of the formula, take the function, well, actually take the flipped function, put it through the channel and evaluate at 0. This defines a linear functional. And this linear functional can be used to recover the whole operator, the whole channel, the whole system by a convolution operator, which at the moment is just written as apply mu to the shifted version of the flipped f in order to get the output. So T mu of f is the output under the system convolution by mu of the input signal f at the position y. Now, these continuous functions with compact support are also not only signals, but they also can be interpreted as measures. We can integrate in the ordinary way with Riemann integrals an ordinary function f of x, a signal f of x against such a k of x function, and that gives a linear functional. We have verified that these so-called nice measures are, with density k, they are also bounded measures, and the norm of the bounded measure, which we often describe as mu sub k, is exactly the L1 norm, and the L1 norm is the area between the graph of absolute k and the function and the 0 axis. Another very important class of measures, of functionals, is the so-called discrete measures. They are finite linear combinations of point measures, and for them, the norm is just the absolute sum of the coefficients taken in the natural representation, so avoiding duplications of the xk. Now, having two nice subfamilies, subspaces actually, of discrete measures or nice measures, we can always take the closure. We have identified already the closure of the finite discrete measures as the bounded discrete measures, which simply means you take the absolutely convergent sums, so infinite sums, but still with finite total masses, roughly speaking, the idea. And we will come to the closure of the nice measures, and we will call it L1 during this course or so. The important fact from this identification of linear functionals with on C0 with operators commuting with translation is the possibility of introducing a multiplication. It's quite obvious that the concatenation or composition of two linear systems both of them commute with translation is also, again, a system having the same properties. Therefore, there must be a uniquely determined linear functional which represents the concatenation of two convolution operators. That's what we call mu1 star mu2. And we have to use the above formula of how to get from system to functional and functional to system to actually compute and decide what this convolution is. We have seen that ordinary point measures correspond to simple translation operators. Therefore, for discrete measures, it's quite clear as limits of finite linear combinations of such objects that they will commute. But it was a little bit more work to find out that by the right way of limits, taking limits in the sense of the action on a signal, so deep psi mu convolved with f converges to mu of f by making the partition of unity more and more refined. So using this property, we were using commutativity. So we are getting the bounded measures endowed with the convolution as an internal structure, has the structure of a Banach space, which is an algebra with a norm which is compatible with the algebra, of course, because clearly the norm of a product of operators is controlled by the product of the two norms. That's why we get the measure norm of mu1 convolved with mu2 is at most the measure norm of mu1 times the measure norm of mu2, and that's the decisive law for a Banach algebra. We also have associativity, commutativity, and all these things. But in the last session, we have also found out the different possible interpretations of signals which arise by pointwise convolution or by action of a measure on a test function, or different measures, for example, taking two functions, turning them into measures, or first convolving the functions as functions and then making the result to a measure. They're all compatible, and we will do a little bit more in this direction also. Now, I have already told you a little bit about the basic facts about the Lebesgue space. So L1 in the traditional approach is the space of equivalence classes of absolutely integrable measurable functions. Equivalence relation is the coincidence of two functions up to a set of measure 0. Think of sets of measure 0 as small sets. Clearly, finite sets, countable sets are sets of measure zeros, but they don't have to be countable. They can be much larger and still have measure 0. So it's, well, you can say it's, you can get used to it, but in a way, I think it's not a very natural concept if you start from scratch. For us, it's much more natural to say, well, we have already a Banach space, the bounded measures, and we have inside of these a copy of our continuous functions with compact support. They were quite useful for many things. So let's take just the closure of all those measures induced by the compactly supported continuous functions. So I would say inside of the bounded measures, you have the nice measures, and you take the closure of the subspace of nice measures and you call it L1. And so let's try to identify this space a little bit and establish a few properties or so. Recall that we have used already earlier the fact that a measure can be built up from the local pieces. So if you take a measure, mu, you can localize it by a partition of unity. You can take mu psi I, and the sum of mu psi I is absolutely convergent. Actually, the sum of the norms is the norm of the sum. So the norm of mu, it has pieces, mu psi I, and the sum of the norms is exactly equal. I mentioned already several times, this is the analog of the sigma additivity in measure theory. Now, inside of the bounded measures, as in many other translation invariant spaces, we also have a space with continuous shift. So I'm not sure if this is a good symbol. It's an ad hoc symbol. I call M sub BC on the proposition 3, the bounded measures which have continuous translation. And continuous translation means, well, you can shift a measure either by direct definition or by convolving it with a Dirac measure. Then you take the difference to the original measure. So it's a difference of two bounded measures. You can measure it in the measure norm. And you're asking that this will become small if x is small enough or near zero. And the claim is that this is a closed ideal in this algebra. Now, what it means to be closed is hopefully clear. If you take a sequence of measures having this property, the limit measure will also have this property. And this is a simple 3 epsilon argument, which I leave to you as an exercise. To prove that it's Banach, that's an ideal, is something that we will do later. Finally, the claim is that L1 coincides with this subset of continuous shift. In my script, I also mention a little bit the classical notation. Measures in 1D can also be described as Stieltjes integrals with respect to functions of bounded variations. And I think in 1927, Plessner was showing that those measures which have bounded variation where the variation norm of the difference goes to zero are called absolutely continuous. And absolute continuity is a classical concept, which I don't go through here, but which turned into absolutely continuous in the sense of measure theory. So somehow we have a very general and I would say functional analytic view on L1. L1 is the space of absolutely continuous measures. In measure theory, absolute continuity appears in a different way. A measure on the real line, let's say, is absolutely continuous if and only if a set of measure zero with respect to the Lebesgue measure is also a set of measure zero with respect to this special measure. Clearly, in the sense of a Dirac measure, a counting measure, let's say at zero, as a measure would say a set has measure 1 if it contains 0, and it's having measure 0 if it does not contain 0. So that's a simple, 0-1 game or so. Now, if you just take the single point consisting of 0, in the sense of the counting measure, of course, it has measure 1. In the set of measure 0, clearly it doesn't have, it has, in the Lebesgue measure, it has measure 0. So clearly it is not absolutely continuous. We will see, we have several arguments. It will essentially tell us in our terminology that the Dirac measure, which we know already, is not in L1. So clearly it's not induced by continuous functions with compact support by a nice measure. But even if you take limits of nice measure, you never get the Dirac because we are taking limits in the norm sense and not in a weaker sense, as we will see later on. So let's see what the arguments are for the coincidence of L1 as defined in the red definition. So it's the closure of the nice measures induced by test functions with compact support, or the continuous translation. So the easy part is, or harmless part is, take an L1 function and try to show that it induces a measure with continuous translation. Now, because we are taking the closure of nice measures, it's enough to prove it for continuous functions. So if you look for the continuous functions, what you have to do is to show that the measure introduced by the shifted k minus the measure from k in the measure norm goes to 0. But we have seen that for those measures, you just take the ordinary functions, take the L1 norm in the sense of Riemannian integrals, and you have to prove this. So why is this going to 0? And the answer is very easy. You have uniform continuity. So if you shift such a function a little bit only by x less than delta, you're staying in an epsilon strip around this function. So look down formula 77, tx k minus k in the subnorm, this goes to 0. But now think of the L1 norm. Well, the area is at most the size of the basis. So if you're in RD, you have the volume of some cube, which is large enough to contain not only the K, but all the, let's say, harmlessly shifted elements of K. They all live in a joint box. And so if you put the volume here in front of the sup norm, you can control the L1 norm. So the harmless embedding of continuous functions with compact support into L1 and the uniform continuity give you that you are inside MBC, because MBC, I was saying this is an exercise, is closed. So if the nice functions are okay, you can take limits and it will be still in the closed subspace of continuously shifting. Now, in the opposite, for the other thing, for the study of the bounded functions with continuous shift, I would like to concentrate on the ideal property. So again, show that it's closed, but then show it's an ideal. What does it mean, an ideal? A subalgebra is meaning that you can multiply internally elements from the subspace. An ideal is a subspace where you can multiply the elements from inside the subspace with arbitrary elements of the big algebra. So we have the claimed closed ideal MBC and the big algebra of bounded measures. So if you take any measure, mu, you have to check whether nu convolved with mu is preserving the same property. And so you have to look at the shift applied to nu convolved with mu. Now, I told you that the shift in the measure algebra is the same as convolution with a Dirac. Actually, there's a star too much in this formula at the moment. But because of the associativity you get, that you can say, no, the shifted version of a convolution product is the shifted, let's say, first factor nu, and then convolved with nu. But then you can apply the distributive law to say, this difference is actually tx nu minus nu, and then this expression convolved with mu. And by the submultiplicativity, you only have to look at the shift behavior of nu times the constant mu. So the first part goes to 0, the second part is a constant, so the product is going to 0. The final step is the step which is maybe the most interesting, which I keep short at this moment. And that's the variant that we have to reduce our considerations to the convolution product. So what we will show is that if you convolve mu with k, then you're getting continuous functions with compact support, and by taking limits, you're still in L1. So any measure, because of the ideal property, will go into L1 by the convolution. But that's maybe less obvious, and I will do this in more detail, in more generality later on. The continuous translation means that the convolution with k minus mu in the bounded norm can be made arbitrarily small. Well, why is this true? Maybe I should add the details very soon. So we have seen that we can convolve mu with k by actually writing the measure mu convolved with mu with the measure coming from k. Now, if we discretize the measure induced by k, we need translation operators. But if k has very small support, all the non-zero translations will be very small. So essentially, you will find out that this mu convolved with g is very close to a finite sum of translates with very small parameters. So what we can see is that continuous shift, so this property that was giving the characterization of bounded measures with continuous shift, implies that you can approximate the measure by a measure kind of regularized or smoothed by a convolution with some continuous function with small support. And this in turn can be approximated by shifted versions with small shift parameters, which means the deviation is very small. But because k is in L1, mu with k will be in L1. So it means if you give me any function which has continuous shift, I am able to approximate it by L1 functions. And now I'm using the closeness of L1 to show that this means that also the limit, which is our mu, will be in this space. So we have now shown a very important thing. And what has been crucial, aside from technicalities, is that inside the bounded measures, every element can be approximated by compactly supported bounded measures. So this property has been useful. You can separately prove that if you approximate a function which has continuous shift, so in MBC, in the same way as we have done it, also all the approximations will have the same property. And then it's maybe more clear why mu, now without loss of generality, with compact support convolved with a test function k with compact support will result in a continuous function with compact support, which clearly is inside L1, and therefore you can take limits. So you see there are some alternative arguments always, and I'm not continuing about all the details. Now, more or less, in order to give you a glimpse on what are basic properties of this now, well, strangely defined L1 space, but I can hopefully soon convince you that it's exactly the space that you learn in other courses. If you multiply L1 with bounded continuous functions, you're getting all of L1. When I write such a product, I mean the complex product. So if you give me any two sets and it's reasonable to multiply the elements individually, then you take on the left-hand side all the possible products of bounded continuous functions with L1 functions, and you get all of L1. Now, this claim has two substatements. One is if you multiply, you're staying inside L1. I think it's quite easy. And if you take constant 1, which is a member of the bounded continuous function, of course, you reproduce every function. So this is not surprising. It's a bit more surprising that if you multiply with C0, now it's clear that you're also staying inside L1, but that you're able to write every L1 function as a function in C0 even, which kind of means that if you give me an L1 function, it has some kind of rough decay, but you can even multiply it with you can find another function which has a little bit less decay, so that multiplying it with a C0 function is giving the original function. Now, a formal proof of the equality, not just the containment of the second part, is following from the Cohen-Ewing factorization theorem. I will cite it several times later on, but I wanted to mention here at this moment. What may help you to understand better the connection to measure theory and to these equivalence classes of measurable functions, or to appreciate it, is the combination of what we know already about L1 with the general functional analytic tricks that we have heard. So for the discrete measures, I was telling you already that with the help of so-called telescopic sums, you can replace taking the closure with taking absolutely convergent sums. So now assume somebody is giving you an element f, then formally I would say the measure that we get from such a one function is the absolutely convergent sum of measures, but absolutely convergent sums of nice measures is the same as absolutely convergent series of Kn, with the absolute convergence taken with respect to the L1 norm. Each individual Kn is a continuous function with compact support, and we can assume that it's the L1 norm is done in an integral way. Now think of this as a collection of positive functions. That's the most interesting part. For negative value, you can even do better. I mean, you get the same result by estimating it from above by absolute value of Kn. And for complex valued functions, you decompose them into real and imaginary part. So think of a pile of functions Kn, which have graphs, which have finite area, each of them. But even if you glue all this together, so you staple one above the other, you're getting still an idea of what could be the integral of the sum of all these pieces. Now, the main point is, in this situation, you will get a measurable function which may add up to plus infinity at very few points. It's very easy to produce individual points, but you can prove, and that's part of Lebesgue integration theory, that you never have divergence on a set of positive measures. So the problem makers are all concentrated on a set of measures 0. And that's how you define this class. F of x can be, and that's justified by measure theory, defined individually pointwise by taking the sum of Kn of x. And with the exception of a set of measure 0, where you can put things arbitrarily, normally people would say, okay, I put 0, then it's a real valued function, and you can avoid the plus infinity value. So, or you may have even oscillations at the set of measure 0. So you just put 0 at all the problem-making points, and then you have a well-defined representative of L1 in the sense of equivalence classes. So this is maybe something that tells you it's rather technical. If you've learned your lessons in measure theory, you know what I mean. If you don't have this background, you don't have to learn it to understand, to follow this course here. Now, of course, the main purpose of Lebesgue integration theory is to write the most general integral in a spirit, in a certain way. So we would expect that now, if you give me a measure mu g, which is in L1, we could find what mu g of k is, even extend it to all functions f in C0, and by the observation of last session, we can extend it to all of the bounded continuous measures. So you could say we have an integral of any bounded continuous function f against any L1 function g of x, and we write it as an integral. People coming from measure theory would say this is a valid integral, but we say it's just the limit of these Riemannian integrals, or it's the action of a measure coming from an element. But we have already seen that we can take any L1 function, we can turn it into a positive L1 function and integrate it in this way, and you will find out that this is kind of meaningful whenever both sides are well defined. So in the Lebesgue sense, the L1 norm would be, of course, the integral over the absolute value. It's also a measurable function. It would be finite. And it is the same as in our case for ordinary nice functions with compact support. So what another form of describing the situation is f. Oh no, it should be not f, but it should be g. So lemma 10 should read g goes to integral constant 1 against g of x dx. So constant 1 is a bounded continuous function. A harmless trivial one is a special case, but now it's well defined not only on CC via Riemann integrals, but it is extending to a unique bounded linear functional on L1. And we can always, whenever we find such expressions, we can always interpret them in such a way. Okay, now comes, I have reshuffled the content a little bit. So at the moment, we're just saying what are the extensions of our bounded linear functional, and I was already telling you that with this trick of applying the pieces to the function h, which may be a bounded continuous function, you get the correct estimate by the norm of the measure and so on. And later on, I will compare it with the with other methods with so-called bounded approximate units. So let me ask, I will take, let us come to, I would say, the heart of the first part of this course, namely the connection between engineering terminology and mathematical approach. So you have seen we have these functionals, we are defining convolution operators or so, but let's look back at the engineering books and how they describe such linear systems or linear operators, time-invariant linear systems. They work with the term impulse response, which is very meaningful in discrete setting, but not so clear here. And I will kind of sharpen your mind by telling you it's almost a complete disaster if you're looking from an extremely pedantic point of view. It's at least a little bit vague if you're describing it with, if you want to know more details. So that's maybe my point of view. And I will, of course, tell you how to get out of this mess, this perceived mess from the point of view of a pedantic mathematician by using the correct mathematics and still having the engineering applications in mind. So the impulse response is you would expect now, how can I get the measure by inserting a Dirac delta into your system? So if it was a mechanical system, you would say, well, instead of exciting it with some kind of vibrator or so, I would try to excite it with a hammer. But we all know that systems only usually behave linear in a certain range. So maybe inputting a delta would just destroy the system or would be beyond the linear range of the system. So maybe that's not the perfect idea. Formally, if you take the first point, delta zero is good. Okay, we know what it is, but it's not in the domain of our Bibos system. We are allowed to insert now bounded continuous functions. Maybe later on we will see we are allowed to input bounded measurable functions, L infinity functions, but can we put a delta? I mean, it's so unbounded, you cannot have anything worse. The other description of linear system is by the transfer function. So I'm using the letter that Helmut Lebesgue is using in his course. So a transfer function describes a system by multiplying the Fourier transform and then going back. So you would say a system which is obtained by taking the Fourier transform, multiplying it, and then taking this back. So you're doing a frequency filter, you're modifying it in the same way as you use your old hi-fi radio to damp the high frequencies or sharpen the low frequencies or whatever. I mean, this is the standard way of thinking about frequencies and changing the loudness of frequencies. So that's the typical filter. So formally, again, delta zero might not be in the domain. Even if we are in the domain, I mean, how are you learning to identify the impulse response? You're saying, well, I have shown you the picture in my script. You're approximating the impulse signal by sum of rectangular pulses. And those rectangular pulses, they converge somehow to the delta. And that means, well, let's put into our system these rectangular pulses. Now you can argue they're still not continuous. So actually, I would prefer to take triangular impulses or Gaussian pulses or so. But you can always compress such signals which have area 1 and compress them, and you would get a delta. And actually, it's important to take anything with area 1 or integral 1 so that you get by compression a unit mass or a Dirac delta, which has this required property of integrating to 1. This is quite a mysterious property if you think of the Dirac function, as it is always often called, as a function which is plus infinity at 0 and 0 elsewhere. Because why is 3 times infinity different from infinity? You would write 3 Dirac at 0. If you take the evaluation, you have 3 times the value at 0. That's quite fine, but 3 times infinity, it doesn't make sense in this way. So what I'm saying is, well, we can approximate the Dirac in some way by a sequence Bn, maybe triangular function, as I said, of area 1, but why can you expect that the output is also convergent? I mean, in which sense should it be convergent? The article, very recent article of Michael Unser, which is at the moment still in the archive, describes the discussion of why are books, often quite well-established books in engineering, assuming that an impulse response has to be an L1 function if it's a BBOS system. And this has to do with the question, well, if you have an impulse response which is a measurable function, more or less, then it has to be integrable. You can take, for example, an arbitrary L2 function and try to get a BBOS system. So you would probably say convolving with the sinc function, which is not L1, it's not integrable in the Lebesgue sense, will not give you a BBOS system. So you may have an input signal which is made up such that it is still a very nice bounded function, but the oscillations arranged in such a way that at the output you get arbitrary large values. So the point is you cannot control the size of the output by convolving a sinc function with bounded functions. So the question is, when and how can you control the output sequences? I mean, to demonstrate that everything is nice for certain input signals is okay. It gives you the feeling that it's not unreasonable, but as mathematicians, we want to know like this. Now, this was kind of on the time side, but now I have to discuss the same on the frequency side and the transition from one to the other. The goal of our presentation here will be, not today, but for the part of the rest of the course, is to say, well, you can describe any system if you do it properly by on the time side as a convolution operator or on the frequency side as a multiplication operator, and they're equivalent. So if you get t of delta 0, and this is a function h or measure, does it have a Fourier transform? We have not still studied this. The other way is if you're having this equivalence. So is it really true that now in this maybe more general and actually will be more general context, you have this equivalence? For me, going a little bit ahead, the Plancherel theorem and the characterization of systems which are in linear systems on L2, which are translation invariant, is a good example. So jumping ahead, I would say we will see that the Fourier transform for ordinary function can be extended to the Hilbert space L2 of all square integrable, Lebesgue integrable function, a very nice object which has a scalar product and so on. And then there it's a unitary operator. So, okay, you can show that everything is nice, and you expect that every translation invariant operator again should be a convolution operator. Therefore, on the Fourier transform side, it should be a multiplication operator. So now, what can you say about multiplication operator? What is the sufficient and necessary condition on L2, the Fourier version of L2, to be a bounded operator on L2? And then you find out it has to be an L infinity function. It has to be a function which up to a set of measure 0 can be controlled by a bound. That will preserve the L2 property, and then you go back with the inverse Plancherel Fourier transform. Okay, so it's quite clear that you would like to say, okay, we know that the operator itself can be described as a convolution operator. Just take the inverse Fourier transform of this bounded function. But now I'm stuck because bounded functions may not have an ordinary Fourier transform. Even Plancherel theorem is not helping us. And we will see the objects will be called pseudo measures. These are just the inverse Fourier transform, or the same as the forward Fourier transform of L infinity, which is the right space for pointwise multipliers. But we need a more extended, more comprehensive Fourier transform, much more general than the one with integrals, much more general even than the one for bounded measures, but still we have to do this. So just the summary of all this. We have a lot of things to do, but we will hopefully be able to find out that t of delta 0 can be given a meaning, and this t of delta 0 will be called the impulse response function whenever we're able to give a meaning, and that the Fourier transform, hopefully also meaningful in the future, will be the transfer function, and so we have to do the frequency version of our function in order to multiply it with this. Now, the justification for this will come in the second part of the course session or so, but I would like to finish the first part before the break by introducing to you an abstract concept. You can forget about it for a while later on, but it's one of those functional analytic tricks which makes proofs quite short, which otherwise would require approximation arguments and well, be more cumbersome, but maybe more elementary. Okay, so what I'm telling you by showing you definition 4 and then the lemma 12, which is just a summary of known facts from functional analysis, is the following. You're giving me any bounded operator T on a Banach space B. So we can think of B being our C0 space, some of these operators. Then there's always an adjoint operator called T prime, which is a bounded linear operator on the dual space. So in our case, it would be now you're turning an operator from C0 to C0 into another operator which maps bounded measures into bounded measures. And the trick is quite easy, that you're composing your linear functional, your element from the dual space, I call it sigma here, sigma in B prime. You're composing it by applying with the T, but of course, you can compose it only in one way. You have three players, so to say, an input signal F, an operator T, turning it into another signal, and a functional. So the only reasonable way to do it is to say, apply the operator to the signal, you get another signal. And then after applying the operator, you get the sigma. Now, from the point of view of linearity, it's clear that everything is okay. This is also a new object which depends on the sigma. So if I would do the same thing for sigma 1 and sigma 2, and I would say now my sigma is sigma 1 plus sigma 2, maybe even 3 times sigma 1 plus 5 times sigma 2, then you would get each time a new linear functional, but this collection of linear functional has again a very natural algebraic structure. So T prime itself is not just T prime sigma is not the symbol for a new linear functional, but you can even read it as a mapping from sigma to a new sigma, which we called T prime of sigma. And because it's linear, it's called a joint linear mapping. Now, if you're playing around with MATLAB, you know already what A prime is. Think of real matrices. You have a mapping which is going, let's say, from R3 to R4. So you are having a mapping which is represented by 4 times 3 matrix. And that matrix has a prime object, and that's is the transpose matrix. And it goes from, it has the opposite of a transform matrix. So you're changing the size parameters, and it goes in the opposite direction. Well, what you would say is the opposite direction of R3 and R4 are, instead of column vectors, are row vectors. So you're essentially multiplying the row vectors from the right with your matrix, or you're saying, no, I don't like row vectors. Vectors should be multiplied by matrix multiplication. Okay, so take the transposition, and that makes out of the matrix the transpose matrix acting now on the transpose row vector, which is the original, which is a column vector, and that's why you have this prime. So it's really the abstract concept of transposition for operators. Now, if you take this definition of definition 4 and you check the size of this new operator, so kind of how big is T prime sigma compared to the size of sigma as a functional, you will be able to control it by the magnification factor of the operator B. So an estimate is quite easy. But it's a fact from standard functional analysis, I should say, the Hahn-Banach theorem that allows you to iterate more or less. You can say, well, I control the size of T prime by T, but then I'm controlling the size of T double prime going from B double prime into B double prime. But the point is, Hahn-Banach tells you that B is sitting, a kind of copy of B is sitting inside B double prime in an isometric way. And that's the reason why you get exact inequality, because you're estimating an object which has equal terms on left and right hand side, so the middle term has to be equal as well. We will take this as granted, but it will be useful. It's more a motivation for what I'm doing in a more concrete way. Now, in order to kind of increase your confusion for a little moment, let me express the fact that we have seen that convolution operators are very nice operators on C0. So any operator has an adjoint, which is now an operator going from measures to measures. So what is the adjoint of a convolution operator viewed as an operator putting measures into measure? And so you see here it's the C nu, but C nu is meant to be a convolution with a bounded measure acting on C0. A prime makes out of this a measure. And the claim is this is the same norm as the original convolution operator, which is the same norm as the of a measure nu, which has the same norm as the norm of the flipped operator. Actually, we will see that the adjoint operator is just internal convolution with the flipped measure. And the good thing is flipped measures have the same norm or the same quality as the original measures. Why? Because they act on the function like the original nu on the flipped function, and the flip doesn't change the supernorm of the function. So we have a nice involution. F goes to F flip on the functions, on C0 or on CB. And we can induce from this a flip operator on the measures. This flip operator, of course, by the way, maps delta of x to delta of minus x. So it replaces the argument or the action from a positive x to a negative x, or from, yeah. And so let me take a break here. Feel free to ask a question in the chat because I will continue with this. And my plan is to come up to the definition of the Fourier transform for bounded measures in the rest of the session. Okay, so I have explained to you what the joint operator is, and that you are doing it just by moving the operator over to the original Banach space. And so the adjoint operator on the functional is nothing else but the concatenation of the operator with the linear functional coming at the end. And that this mapping from functionals to functionals is having the same possible magnification factor or operator norm as the original operator. Now, the key why it's interesting to look at these operators is, these extended operators, is that they are preserving weak star convergence. I will not explain here the details of weak star convergence and why it's called weak star. This is a weird term, but it's just, I would say, convergence by action. So what are measures for us? They are linear functionals. Well, when would you kind of say that a sequence of functionals, a sequence of measurements is approximating a final ideal measurement or so? Then you will say, well, I have to test it. I mean, I cannot look at the object itself. I would like to see what it does on a given input signal. And so the concept of weak star convergence, forget the abstract term, is just whenever you apply it to one of your potential candidates, you observe convergence, and the limiting object is another element from the functionals. This is what you call a weak star convergent sequence. Well, if you recall, we have seen also nets, which means the index set doesn't have to be the natural number 1, 2, 3, 4, 5. It can be the family of partitions of unity, very much like the Riemannian sums. There are good ones and not so good ones. And we were saying that deep psi mu is weak star convergent to mu if you let the partition of unity become more and more refined. Well, what does it mean? It converges. It means that for a given f, the difference will be less than a given epsilon. If you just make sure that your partition of unity is fine, leave alone which partition you choose, how you choose the midpoints and all these things. And now this very natural convergence of measures, and by the way, this is what Dirac measures do. Let's say delta at 1 over n, a sequence 1 over n tends to 0. So you expect that delta at 1 over n converges to delta 0. And we've seen it doesn't converge in the norm, but if you apply it to a test function, f has to be a continuous function, you will see, yes, it converges. So it's exactly the most natural form of convergence for functionals. And now the claim is that adjoint operators preserve this form. So if you apply t prime to the set mu n, so you can think of brackets around this, t prime of mu n is a new measure applied to any C0 function, and on purpose for the proof, I replace it instead of f, I'm writing h. Of course, if you write for every function, you could also use the symbol f, but in the proof it will be convenient to take a different symbol here. Okay, so why is any adjoint operator preserving weak star convergence? So again, you're assuming, I'm using the concrete example to sharpen your intuition. You're assuming this, and then you apply this. But what is t prime mu n of h? It's just, well, recall, you move the t prime over to the argument. So what we have to look at is what you see here in the proof of the lemma. It's t prime of mu n minus h, but you have to rewrite it as mu n of t of h. You can remove some of the brackets, of course. But what do I have to do? I mean, t of h is just another element, so it's why I'm introducing the h. T of h is an element that you can call f. Operator t goes from C0 to C0, or from the Banach space to the Banach space. Therefore, you just say, well, because the measures are mu n are weak star convergent, this also has to be true for this other element, because it's true for every element. So in order to get an error less than epsilon, you choose the index with respect to the input argument f equals t of h and not f originally. But that's all. So it's from an abstract point of view, it's playing around with symbols. So how can this be useful? And I will try to convince you, yes, it is useful. I must say that the two following pages, so 35 and 36 of the current version, so this is more for those who are listening online, are a little bit confusive, and I will more or less skip them at the moment, because I had the plan of proving it first by doing it for Dirac measures, then for discrete measures, and going to the limits, until I realized we have meanwhile enough information to prove it in the more general form. So it's definitely more important in the oral presentation to explain what I'm going to do. So the joint operator of the convolution operator, and that's the convolution by a bounded measure, as we have seen, it defines a linear operator on C0. Well, you should write RD. This turns out to be another convolution operator, but now it's the internal convolution. The only thing that changes is from convolution with mu, you get mu flipped. So in symbols, C nu prime, you have to read, it's not C prime nu, but it's C nu. The convolution operator is an operator acting C0. The prime is an operator from this is convolution, but now it's internal convolution with the nu prime. Maybe I skip first the argument, but for explanation, I'm saying, well, let's try to do it. And that was my intuition first. And it's always a good idea that whenever you want to prove something for general measures, try to prove it for simple measures. And if you need it for simple measures, you can reduce it very often to Dirac measures, and then everything should be harmless. Or you are able to reduce it to nice measures. Then you can use Riemann integrals, interchange, transform, and so on. So we want to understand what is the adjoint action of delta x as an operator on C0. And we know this convolution is just a shift operator. And how is this acting in the adjoint version on the delta y of f? Okay, so the main point of this line, so of formula 87, is now we want to understand how these abstract formulas realize in the concrete setting. So whatever operator you have, here it's convolving with delta x on C0, what you have to do is throw it inside the bracket. So apply it first to your input signal. So we have delta x with f, and then apply your measure, which in our case is delta y. Okay, now we know that convolving the delta is just a t of x, so it's a shift operator. We have established this already. Okay, we have to evaluate at the point y the shifted version. So this is, of course, inserting the variable argument y for fixed point f of y minus x. What is it? Well, this is the evaluation of the function f at the position y minus x. But we know that the product of two things is a convolution of two measures. Recall, we want to come out with something that acts on our input mu, and our input mu is the delta y. So we hopefully can write it as an internal convolution now. So this is the convolution relationship between Dirac measures applied to f. Now this is true for every input signal f, and that means these two functional, the abstractly defined functional adjoint action operator on dy, or the concrete is internal convolution with delta of minus x. So in symbols, it means the adjoint action on delta y is the same as the convolution with the flipped version of the delta, because the flip is an operator that you can apply to any measure. Recall, mu flip of f is by definition and for many reasons has to be mu of f flipped, and so you can reduce it. Now, I was playing around, but I don't want to do this with approximations or so. You can imagine at some point I wanted to use the discretization of the measure and then flipped, and had to compare it with the discretization deep psi of the flipped measure. So formula 89, I have established it if you take a partition of unity which is stable with respect to flip, which simply means let's take the triangular function. The triangular shape might be from -1 going up to 1 at 0 and then symmetrically down. That the psi would be symmetric, and then you would have this formula which would make certain things easier. But at the end, I realized we don't need it. I mean, you have to have discrete versions of what you want to prove, and then you take limits. You see, that's what I did, roughly speaking. Probably it's interesting to take a look on what the arguments are, but I don't want to do it here because I found a better way to explain it. So the proof will be actually the proof of proposition 5. So proposition 5 in this version of my script is now exactly proposition 4, but with a short and more elegant proof using what we have already. And already earlier, I was showing you lemma 14, which means the flip operator is compatible with convolution. Here we are showing that if you introduce new flip on measures and f flip on functions, of course you can also convolve a function f with a measure and then flip the result. Maybe one should argue that in non-commutative groups the flip changes the order, but we are on a commutative group, RD is commutative. So we can use this formula, and that's more or less what we need, plus our translation formula. So I think for now it's very important to go very slowly through this argument in the proof of the proposition. So again, the statement is a joint action is just convolution with the flipped measure. So I'm starting with the definition. The convolution operator adjoint means you put, very much like I did it with Dirac, now with abstract measures. But then comes the formula that we have had already before. Mu applied to nu is just a functional and related to a convolution operator. So it's the convolution operator with mu, but applied to not nu with f, but to the flipped version of nu with f. And then this is an input signal under one and another convolution operator with some flip in between. So it's a signal, and that can be evaluated at 0. So this is just the basic relationship between a functional mu and the convolution operator mu star. But now I'm inserting this flip property, and I say, well, we have established meanwhile associativity in the most general way and the flip compatibility. So nu convolved with f is the same as nu flip with f flip, and we can put brackets in a different way. But we also have commutativity already. So instead of mu with nu flip, we can write nu flip with mu. And then we have a new action, which is directly related to mu and nu, only the flip has been introduced to f. So if you read from the beginning to the end, the observation is there's an abstract functional obtained by the joint action of the convolution operating by nu on the mu. But what it does on a given f is the same as just take nu flip convolved with mu on each of the functions. So we have established exactly the red relationship in the proposition 5, so formula 39. Sometimes for the future, it will be more useful to have the flip on the other side. So just take the formula, replace the nu by the nu prime, nu flip, sorry. And then of course you have to use nu double flip is the original flip. So if you use the second and the last term in the blue formula and replace nu by nu prime, you get a very useful formula that mu applied to convolution is the same as nu with mu applied to f. So this, for me, the motivation was I wanted to tell you, well, the adjoint of a convolution operator is again a convolution operator in a somewhat different setting. Such a adjoint operator has better properties. So actually we expect now that a convolution operator must have these good properties also, and that will be helpful in understanding the convergence issues for the Dirac sequence. So why everything is in a way well justified, except with different mathematical tools. So what is my claim? Based on this observation, I mean, I would say from the abstract point of view, this is just a combination of the two observations that we have. We have identified the adjoint operators, and we know that adjoint operators are good. They preserve weak star convergence. But you can do it now directly or so. So if you're saying, well, I'm interested, and so it's really the red formula above number 94, which is used, and you can forget about this adjointness business if you are not familiar with it or if you don't like it until now. You will see it's useful also in the future. So we're saying, assume you have a weak star convergence sequence mu n to mu 0, and now you convolve everything with another bounded measure called nu. So what we have to do is to let nu convolved with mu n act on f. And now I'm just using this formula above and say, well, this is the same as my mu n applied to nu flipped with f. And you see this is the kind of the joint action on the f. And this is just another element. So nu is known, nu flip convolved with f is one f0 function. It's like the h that we had before. And because for every function h in C0, everything is convergent, also for this one, it's convergent to mu0. And then I'm writing it back as nu convolved with mu0 applied to f. So it's no magic once you have this formula, but somehow also this formula has to be verified. I mean, you see, there are a lot of possible connections between the different terms. For a course like this, the challenge to the lecturer or to me now is to find a short path which is not obscuring what's happening. So sometimes there are short ways where you don't, it's like magic. So you're getting formulas which you have here, you cannot understand them. I try to go and not the shortest path, but the one where you have the biggest sight on the environment and where you see most of the things. Okay, so now let's look at the situation that you encounter in the standard engineering courses. So assume somebody is giving you a BIBOS system. And again, later on, we will discuss the case where you have other systems which are not BIBOS systems, but for now it's, and somebody is giving you a sequence Kn of nice functions, which are supposed to be weak star convergence to the delta zero. We will see a lot of such things. So again, for now, the triangular functions would be the best example. They should have area 1, all of them, they are compressed in a way that if you compress them by a factor of 5, then everything is smaller by 5, and therefore the height has to be comparatively larger and expanded by 5. So yes, in this case, it's true that the values go to, at 0, go to plus infinity, but you can have other examples that we'll see later. So we have a lot of such sequences. They all have area 1. If they are non-negative, you just assume that they are having integral 1, and they're approaching the direct measure. And then, of course, you can look at T of Kn. Kn is both a measure, so as a measure, it has mass 1, but we can look at this as an input function, and you can throw it through the channel. And now what we know is the operator T, it's not only measurable, mapping C0 to C0, but it's also mapping bounded measures into bounded measures. But actually what we throw in is an L1 function. So we have Kn is in L1, and we have characterized it L1 as the space of continuously shifting functions, or at least we have shown that L1 is an ideal. So whatever mu you apply to such a Kn, you end up in L1. And so we are getting a sequence of functions, which is not surprising. After all, we were getting continuous functions, but they're not only bounded as functions by the size of the input function, but you know, they are exploding. So it's not very helpful, but we control them by the area. So again, we are going from L1 to L1. But viewed as subspace of the bounded measures, as bounded measures, they are weak star convergent to the delta. And the output therefore has to be also weak star convergent to mu convolved with Kn, which is mu convolved with delta. So maybe look at the paragraph here. We look at Tkn. We know now that every such operator is a convolution, and by identification of all these different concepts, you can say we take it as a convolution with mu Kn. The mu Kn, I mean the Kn are bounded in the L1 norm, therefore the mu Kn are bounded measures, and convolving with this is going to the limit, mu convolved with the limit of the Kn, which is the delta zero. but delta 0 is the shift operator. So I'm saying, okay, the limit is mu convolved with shift by nothing, which is identity, which is mu. Great. So we are seeing that it is justified by this jointness relationship, or by the formulas which kind of contain the information that every operator, which is a convolution operator, is also an adjoint operator and therefore preserves masses. That in this way you can guarantee that the output of a sequence TKN is also convergent, but the form of convergence is the weak star convergent. So clearly, this raises the question of what does weak star convergence mean. We will see what it also means to the transfer functions and all these things. But I think that's already an important issue. And I would like to just mention that the whole thing is quite consistent. Convolution operators acting on L1, it's just a subspace, might be a little bit smaller, but no, it's the same as the convolution operator of the internal convolution, which is the same as the size of the flipped function, flipped measure, which is an element of the bounded measures, which is the size of the original measure. And so one is the joint of the other, and so on. So, and if you flip measures individually, you can do it like this. And so we are in a very comfortable situation or so. So whereas my summary is, whereas in the engineering literature, everything goes by example, or just everything is done in the discrete setting where the Dirac delta is just a unit vector at 0, so to say, on the integers, for example, we do have to deal with the weak star convergence. And we see that this limit is okay in a better way. Now, I'm not sure. Yeah, maybe I mention it. There is a theorem called Wendel's theorem, which starts to discuss what are the bounded linear operators from L1 to L1 which commute with translation. And then it turns out they're exactly the same thing. You are showing that you have to input a sequence which is convergent to Dirac, and then you know that the target space will be also bounded in L1, but bounded in L1 means bounded in the measure space. And then another functional analytic principle is used, which is the fact that in a dual space, a bounded set has a weak star convergent subsequence. So somehow this helps you to identify your operator as a convolution operator. So actually every translational invariant operator from L1 to L1 is a convolution with a bounded measure. We know already part of this, namely every bounded measure defines an operator on L1. That was the statement that L1 is an ideal. And so somehow Wendel's theorem is a converse to this theorem in a different setting. But L1 and C0 are very specific cases also. Now, I would like to tell you a little bit about some general kind of background information. I try to be not too pedantic, but also to tell you where you have to be careful. I mean, when you're saying translation is the same as convolution with a Dirac measure, then you may have different viewpoints. One possibility to extend it to measures, so to ask what is Tx of mu, would be to say, well, let me try to approximate a measure by ordinary nice measures. So you have a limit. Mu is the limit of measures Kn, like the Dirac, and then you shift those measures upon these nice functions, and you ask, does it have a limit? Now, in this way, you would say, well, I'm integrating Tx Kn against a test function Fn, and then everybody writing out the integral would say, well, in order to reduce it to to the argument, to the unshifted version of Kn, Tx of Kn as a set is Kn of z minus x. You transform the integral back so that you get an action. So you would argue that Tx of mu applied to f should be the same as mu convolved with minus x. But due to this weak star limit business or so, I just want to tell you, you can take any viewpoint. You can say, well, I approximate the things that are more abstract objects now by simple objects, but I have to do it in the right way. It has to be in the weak star sense only. Then I know what the new extended operator is, let's say translation to a delta. And then of course you find out that Tx of delta at 0 is T of delta at x or so. Or you do it in a simple duality trick and you're saying, no, I just would like to say I have to convolve with a delta, and that's also okay. So again, referring to this trick with the convolution, Tx of mu, if you would say this is something that is acting on the measure, so it should be delta x convolved with mu. But that by definition is, there's a convolution sign missing in the second and third term. It should be mu convolved with delta x flipped convolved with f. But delta x flipped is delta of minus x, which is mu of t minus x of f. So the red part shows you that if you want to have a very simple definition of a shifted version of the measure, you can do it by just saying I'm taking the opposite shift on the input argument, and in this way I'm moving my delta. Also, when you think of the Dirac and you want to move a Dirac, let's say 5 units to the right, in order to get the function value at 5, of course you can say, no, I prefer to keep my machine, which is picking values at 0, which is a delta 0, but I shift my function f so that the position at 5 is getting the position at 0. So this is kind of what physicists are doing all the time to say, or you have a plot and say, let's put the origin at this place, at the right place where I'm picking the value, and that's what you're doing. Okay, then another statement which I think is a little bit redundant now is that if you do this convolution operator, now it's a convolution operator with an ordinary function from the right. It also has some form of continuity, but I think it's boring to do this now. So in this sense, we have now finished this discussion about convolutions. All different convolutions that we have are fine. They are following a commutative law. They're following an associative law and distributive law, of course. So if you mix addition with convolution, everything is fine. I would like to mention that people who have studied distribution theory and who try to define the convolution of distributions in the most general way, and I would say in a very individualistic way, they can come up with examples where you have 3 distributions or generalized functions where by specific mode you define, let's say, sigma 1, sigma 2, sigma 3, and you're computing sigma 1 convolved with sigma 2, and then the result with sigma 3, or you convolve sigma 1 with the convolution product of sigma 2 with sigma 3. So you're looking whether the associative law is valid, and then they can come up with examples where this is not possible. So I think these situations are rather pathological things. It's where the corresponding convolution operators are definitely not operators from, do not correspond to operators between spaces which you can concatenate, and that's will not play a role. But on the other hand, to loosely play around and say, well, whenever you're using a convolution symbol, you can use all the laws. I would just tell you, well, if you have the solid mathematical basis that I try to provide by this course, you can do it and everything is justified. If you're not sure, you should try to use arguments like the ones that I have shown you. And I think in 99.8% you will succeed. If you have troubles, maybe you can consult me. But you should not say it's almost clear, it's an automatic, because you've seen we have different kind of convolution. A measure with a function is by a different way as convolving ordinary functions or indirect ways of convolving measures which represent systems and so on. Okay, let me take a break and tell you we are going now for the Fourier transform, and just start this direction, and we will do it next week in more detail. So for a long time, my viewpoint was that I take L1, as my advisor was suggesting it, as the starting point. L1 is a Banach algebra with respect to convolution, which is kind of clear because it's inside bounded measures, and even L1 with the bounded measures is in L1. So if you L1 with L1 must be in L1. But also Lebesgue integration theory tells you, yes, you can write the convolution integral pointwise almost everywhere. You have the right estimates. I was mentioning this before. So then let's look at this natural object of Fourier analysis. What is the corresponding Fourier transform? And very often you find the term of spectral analysis and spectral synthesis. If you go for the classical situation, which is Fourier series expansion, which was created almost 200 years ago, you would say, well, we are going for the goal of writing every periodic function as a superposition of pure frequencies. So this is the synthetic part. If you give me coefficients, I can synthesize certain periodic functions. But of course, the question is then, but can I get every periodic function? And now it depends extremely on the setting, but if we are able to introduce a Hilbert space structure, and then that came out, let's say 100 years ago, at the beginning of functional analysis, you have to work with the Hilbert space of square integrable functions, which are periodic. And square integrability, of course, refers to integrability over the one period. Then the pure frequencies, which are indexed by the integers, are an orthonormal basis. And if you think of orthonormal basis in R3, oh yes, it's easy to write a vector with coordinate 1 to 3. You just project that vector onto the coordinate systems, then you get the coefficients that you need. Now everything is quite a bit more abstract, but we have the same abstract structure of scalar products of functions, which means you integrate one function against the other. The second one, if it's complex valued, is taken in a conjugate way. So it's like this Euclidean scalar product for Cn, complex space or vectors, column vectors, but now in a continuous version. And then you verify that these polynomials, these trigonometric polynomials or complex exponential functions, according to Euler's rule, are forming a nice orthonormal basis, which is even complete, which means nothing is left. It's a different term of completeness. Nothing is left. So really every L2 function is having a representation. And how do you get the coefficients? By taking scalar products. So you have to integrate the pure frequency against the function that has to be expanded. Now, the part where you extract the information, where you do the analysis of the given signal in the hope that you can reconstruct it from those coefficients, from those values, is called the Fourier transform. So applying the Fourier transform as we say it, or the same as correlating the function f with the pure frequencies, and we'll discuss them in great detail, well, means that we are writing the scalar product. It's a kind of L2 scalar product, but the problem is the exponential functions are not in L2. And that's why you have this integrability constraint. Clearly, the absolute value of an exponential function is just 1. So the absolute value of the integration term is the same as the absolute value of f. And that's why the L1 condition comes in completely natural. if you're going to, and that's a conditional statement, if you're going to explain that the Fourier transform is an integral transform. So it's correlation, and you're trying to say, well, I try to see the similarity, how much of this frequency is in the signal. And now the question of Fourier synthesis is, can we reconstruct? And the inverse formula that you learn here, you very often viewed as a continuous limit of inversion formulas for Fourier series would be, well, f of t should be the integral. And if you look at the formulas, there are two remarkable things going on. You're changing for the inverse from the plus 2 pi I to the vector itself, to the pure frequencies. And you're, well, hoping that the integral exists, let's say. Now, if the function f is in L1, the Fourier integral in the sense of Lebesgue will exist. If it's even better, if it's a continuous function with compact support, you can compute the Fourier transform with this normalization with the 2 pi and the exponent by taking a Riemann integral. But in both cases, it doesn't help you to use Lebesgue integrals. You will find that the Fourier transform may be not in L1. So you can have an ordinary box function, you get a sinc function, and this is not, it's nicely integrable, but this is not in L1. So you have to see how you can get back and how to give a meaning to this. That's one of the things that we have to do. The other thing that you can learn from the ordinary function space case is that this integral transform is compatible with convolution. In other words, it turns out to multiply, to turn convolution into a pointwise multiplication, or in different form. If you write the heads, you have this version of the convolution form. Now, I'd rather want to try to explain to you what the goal is for the next session, and that's the Fourier transform, which I have to still to define, is supposed to be an injective mapping which maps bounded measures into bounded and continuous functions, which replaces convolution as a multiplication by ordinary pointwise multiplication. And moreover, we have seen it's a commutative algebra, which was not completely obvious in this case, but it's obvious for pointwise multiplication. So sometimes people are showing that there's an inverse transform, but it's not obvious, as you could see from the examples before. And then a commutative pointwise multiplication would have to go into a commutative star operation convolution. But I take this more indirect. I think the approach with the deep size is useful and helpful anyway. Now, I will try to give you an idea of how we will proceed. And the first thing is, maybe I show you this line here, the pure frequency. So what is a pure frequency? A pure frequency is an expression of the form exponential function with the argument 2 pi I s multiplied with t. It's a tradition here. I sometimes write a scalar product explicitly, so it's a dot product. So you should say it's, for example, in 2 dimensions, this should written be as a bracket with s1 times t1 plus s2 times t2. So we will see when we are doing image processing that these pure frequencies are actually, if you take real imaginary parts, they're so-called plane waves. And these plane waves are controlled by a parameter S1, S2. And that means a vector in R2. So we have the k-space, the frequency space for 2-dimensional signals. And of course, you can say, well, how can I describe plane waves? Plane waves can be either described as ordinary products of pure frequencies in 1 dimension. That's how we would like to understand them and how to work with them. But if you visualize them, you would say, okay, plane wave, either it is something like an object which the graph, you take a real part, has ripples, really a plane wave. So it has a direction and it has a frequency, I mean, how much it oscillates. And you can imagine that S, the parameter S, is a vector in the plane. It has a length. And the length is telling you how many frequencies you have. Going to infinity with S, so making S very large, you have very fine ripples. But still, the vector S has a direction. And the direction is the orthogonal direction to the plane wave. So if a plane wave is constant in one direction, the corresponding parameter S will be perpendicular to it. And there are very good reasons why everything is like this, but that's just giving you an idea. So whenever we write RD, you should think it should be read as an iterated integral over D components, but I think this compact notation is much more useful. And for a beginning and for a first understanding, it's also okay to just use this ST as an ordinary product or so. Now, what we will use is the fact that the characters, so these complex exponential functions, are, first of all, bounded continuous functions. That's why I wanted to have, it should be possible to apply a functional mu also to bounded continuous function or to convolve it as we have done it before. And they satisfy the exponential law. So we all know the exponential function has been introduced, let's say, for biological growth. The growth after, let's say, 5 years is the same as the growth after 3 years, followed by growth of 2 years. And you can take every point as a new starting point, blah, 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 and so on. So what is a shifted version of chi-s, or a convolution with a delta? So this is really the elementary property that we have to understand. Now, a shifted version of chi-s at a point set is, by definition, the character at z minus x. So instead of the argument set, you're diminishing it by x because you have the tx here. But by the exponential law, you can split this into chi-s of minus x times chi of x of, and of course it should be set now. Yeah, so the second argument should be set, the one that is appearing at the end. But then you write out it's e to the 2 pi I. So you would say, okay, I understand. The shift operator has these exponential functions as eigenvectors. And the moral will be, we're really doing a diagonalization of our convolution operators, and I will demonstrate it also with MATLAB. But this is the key property of pure frequencies. Pure frequencies are just multiplied, if you write them with exponential functions, by some numbers each time you're translating them. And that's true for every shift parameter. Now, if you're saying, I know what happens with the convolution operator with the delta x, you know what happens with discrete measures, and what you have to do is to go to the limit with deep psi mu or so. And just to show you what we are doing, no, I have not done it. Maybe I keep it as a secret. Yeah, I don't find it, so please just look at this statement. We will study the Fourier transform on the bounded measures, but if we restrict it, we will end up in the space of C0 functions. So this abstract Fourier transform made more concrete, back to the integral transform, will give C0 functions, which is a theorem known as the Riemann-Lebesgue lemma. And as I've seen in the course notes of Professor Lebesgue, this is stated as a fact which is not proved in detail. So you will see at least some key arguments that allow you to justify this. Thank you for your attention, and I close the session now.